Hi, this is a lecture for the one who missed today's lecture. Today is November 25th, and this is the last lecture. It's about energy balance on reactive process. There's a two method to calculate the delta H dot. One is a single reaction method. Second is a multi-reaction method. But difference is for the first method we use heat of reaction, and for the another one we don't need to use heat of reaction, but we need to use heat of formation. You will see the example of both case later in this lecture. Just for the reminder, heat of reaction is a definition is a heat required to form species at 1 atm and 25 degrees Celsius. And we discussed about this one in the previous lecture, basically delta H naught R. So heat of reaction is sum of nu I multiply delta H naught I F. That means the corresponding stoichiometric coefficient multiply heat of formation of species as standard condition. If you do calculate this one as you've seen it in this example, the number you get is going to be heat of reaction. So bottom line is heat of reaction include heat of formation information. So let's take a look at the example. First example we'll see is example 9.5-1, that is energy balance on ammonia oxidizer. And second example is 9.5-2, that is energy balance on methane reactor. And the difference, as you can see here, for the second example, we have multiple reaction 1 and reaction 2. And for the first one, we have only single reaction. So you will see the different method that I mentioned here. You will see the difference of these two methods. So actually, let's start with the example 9.5-2 first. I read the problem. Methane is oxidized with the air to produce formaldehyde in a continuous reactor. A completing reaction is the combustion of methane to form carbon dioxide. First reaction, we have methane gaseous phase react with oxygen, produce formaldehyde and water as a side product. And second reaction, we have methane react with oxygen, produce carbon dioxide and water. As you can see, second reaction is completed reaction since we have product as both stable material, and first reaction is incomplete reaction. A flowchart of this process for an assumed basis of 100 mole of methane fed, so this one, to reactor is shown here. So here is a flowchart is already completed, so we don't need to do material balance. So I'll solve this one for you. So here is the answer. Here's a 9.5-2 energy balance on methane oxidation reactor. This is basically same diagram, use a SAR. Right, here's we have reactor pipeline 1 and pipeline 2, pipeline 3. We have pipeline 1, the methane coming in as 100 mole, and the temperature of pipeline 1 is known as 25 degrees Celsius. And for the pipeline 2, we have oxygen and nitrogen coming in. We have 100 mole for the oxygen and 376 mole for the nitrogen. And then we know the temperature of pipeline 2, that is 100 C. And for the pipeline 3, as a product line, we need, so the material balance is already given. So we have methane and formaldehyde, carbon dioxide, and water, oxygen, and nitrogen as given as 60, 30, 10, 50, 50, and 376 mole. And the temperature of pipeline 3 is known as 150 degrees Celsius. And reaction 1 and 2, I just repeat the reaction, the writing down. Right, here's methane, reacted oxygen, produce formaldehyde and water. Methane, oxygen produce carbon dioxide and water. So our goal is find out the Q, right? That's our goal. If you see a problem again, it asks completing reaction in combustion. Okay. So the goal is to find out the Q as you see here. So to find out the Q, as we learn, as we learn on the energy balance, Q minus WS, that is the shaft work, it is equal to delta H plus delta EK, that is a kinetic energy, plus delta EP, that is a potential energy. So in this application, there is no kinetic energy and no potential energy and no shaft work involved. So these three terms goes to zero. So delta H is basically same as Q, that's our goal. So we just need to find out the delta H. And then as we learn, so this is a general equation for the delta H that you can use. So delta H is a sigma N out multiply N head out minus sigma N in multiply N in. So our goal for now is find out N and H for the all term. And so to do that, we need to find the NH table, right? So here is the NH table. We have reference, species, phase, N in, H in, N out, H head out, right? So species, as you see, we have methane, formaldehyde, carbon dioxide, water, and oxygen, nitrogen. So you're just writing down here, right? And the phase you writing down gaseous phase, gaseous phase, gaseous phase. Here is since this is water, vapor phase, and here's a gaseous phase and gaseous phase. Since we're gonna use the heat of formation method, which reference is a 25 degrees Celsius and 1 atm, we choose reference as 25 degrees Celsius and 1 atm. For the N in and out, it is already known, the information, right? So we just plug in the number we know. For the methane, we have 100 mole coming in, as you see it here. And then for the coming in, there is no formaldehyde, no carbon dioxide, no water, right? As you see it here. But we do have oxygen coming in, 100 mole, and nitrogen coming in as a 376 mole. So you're writing down here. And for the N out, so you're writing down, so we have methane coming out 60 mole, 30, 10, 50, 50, 376. So you plug in the number here. So now, so we need to find out the H head in and H head out. So for this, since this is a zero, we don't need to find out this term because it will be zero at the end. So you cross out these three terms. So then the H term we need to find out is H1, H2. So we just name it. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this 9 H hat term is our goal. Before we moving forward, we need to find out the condition, temperature. We need to know. For the H1, you see the condition is 25 degrees Celsius for H1, right? So you're writing down here. And for the H2 and H3, which is this one, as you see, the temperature is 100 C. And for the H4 to 49, the temperature we set here is 150. So basically, as we learned, H is an enthalpy, which is a state function. So from where to from condition 1 to from condition 2. So condition 1 will be this, right? So reference state to 25 degrees Celsius. For this, reference state to 100 degrees Celsius. For H4 and 9, the enthalpy we're gonna calculate it from this reference condition to 150 degrees Celsius. So let's find out H1 to 9. This is just review to find out the delta het I. So H is enthalpy, het is a specific, right, per mole or per mass. I is a species. There is a two method we learn. One is a path method, the other one is a heat of formation method. Path method is usually useful if there is a phase change involved, or another, otherwise heat of formation method is preferred method. So if heat of formation method, basically H hat I is delta H naught I F. So this is change delta from where to where. Enthalpy is whenever you see naught, that means 25 degrees Celsius, 1 atm, I is a species, and F is a heat of formation. So this is a heat of formation. So yeah, there was an alarm set. So heat, the H hat I can be calculated by the heat of formation method. This is a heat of formation plus integration 25 degrees Celsius to our desired temperature. Why 25 from 25 degrees Celsius? Because this, we set our reference as 25 degrees Celsius, right? So integration 25 to our desired temperature Cp dt term. So this is an equation we need to use to find out H hat I for the species. So heat of formation method we can find out from table at B1. And this integration 25 to desired temperature CPdP term, we can find out overall this number very easily from table at B8. Or so this table at B8 is only applicable for very selected few gases, and otherwise we have to use CP term, which ABCD term can be find out table at B2. So here, so let's start with checking which species can be found in table at B8. So let's take a look at the table at B8. As you see, this is a table at B8. The title is specific enthalpy of selected gas. So there's a very few gas. So this is H, right? And then you see the reference. This is a reference state. And here we have air, oxygen, nitrogen, hydrogen, carbon monoxide, carbon dioxide, and water. So if you take a look, see this one, right? We can find in table B8, this water, oxygen, and nitrogen. So these four species, we can use table B8 instead of table B2 because that's easier. So for the oxygen, you see this is oxygen, right? So we can find out this H2, H hat 2, H hat B8, H hat 8 from table 8. And for the nitrogen, which is H hat 3, H hat 9, we can find the number from table B8. And for the carbon dioxide, which is H hat 6, we can also use table B8. And lastly, this H water, right? So H hat 7 also we can use table B8. So let's start with H. So we're gonna find out these 2, 8, 3, 9, 6, 7 enthalpy hat. So for the H2, H hat 2, as you see here, supposed to be heat of formation plus integration 25 to desired temperature Cp dt term. Right, so H2 is the oxygen, so I write down everything. So delta H hat not oxygen heat of formation plus integration 25 degrees Celsius to 100 degrees Celsius, because H2, the condition is 100 degrees Celsius, right? And then Cp, oxygen dt term. Where do we find out this information? Heat of formation is basically table B1. So if you go to table B1, right, we talk about, what is it, the oxygen. So table B1, oxygen, you find out, see heat of formation for the oxygen is actually 0. right? So this term is 0, so this 0. And then this term, you can go either way. Both we have both methods. We can use tablet B to find out CP, ABCD term, or you can directly use tablet B8. So tablet B8, if you go tablet B8 for the 100C case, oxygen, and then 100 case, we have 2.24, right? So you're writing down 2.4. Basically, tablet B8 is pre-calculated number for this integration 25 to desired temperature CPDT term. So H hat 2 we find out as 2.24 kilojoule per mole. And then for the H8, that is H8, this one, right? We talk about oxygen from 25 to 150. So 8, you're writing down hero formation of oxygen from 25 to 150 CP oxygen DT term. So here again, from table P1, we already find out that is 0. And then this term, we find out, we can find this oxygen in the table B8, right? So we just need to read the 150 number. So that is oxygen 150 is something between here. So you need to do interpolation between these two numbers. If you do interpolation, you simply, we assume linear relationship. Actually, the actual value is different than this, but we assume this is a linear relationship. So this is a value for the 100C. 5.31 is a value for the 200C. So 2.24, 5.31. You see, right? 2.24, 5.31. So you plug in here, and then we're looking for 150, so it's a between, so divide by 2. So now we have number at 3.775. So for the H3 is this one, right? For the nitrogen from 25 to 100C. So nitrogen, so you're writing down heat of formation for the nitrogen 25 to 150C. Right? Again, this one, we're going to use it for table B8. And then nitrogen hero formation, let's take a look. Here, hero formation B1 for the nitrogen. Here you see the nitrogen hero formation is 0. So you plug in this number as 0, right? And this whole term can pre-calculate it in the table B8. No, this term, right? That is, so we just need to read the value for the 150, right? So you go to table B8, we're talking about nitrogen 150. So nitrogen 150. So it's going to be 2.19. Since this is 150 the between these two values, it is going to be 2.19 plus 5.13 divided by 2, so average. Then if you do that, we have number as 2.19. Am I right? Oh, here's a mistake. I think the value should be slightly higher than 2.9. It should be around 3.5. Anyway, so you plug in the number here, right? And then you get the number should be about 3.5. Let me calculate actually. So calculator, we have, how much we have? We talked about nitrogen 2.19 plus 5.13. So 2.19 plus 5.13, right? Divided by 2. So the value we find out 3.66. So here, this number should be 3.66. Let me type in 3.66. 3.66 kilojoule per mole, kilojoule per mole. Okay. 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 We find out H3, and for the H9, which is nitrogen, we talk about Oh, I see. Actually, this value was correct. H3, we talking about 25 degrees Celsius and 100 C. At 100 C, that is nitrogen 100 C is 2.19, right? So actually, we are right. So we just use this number for the H3 because H3 is, this is a typo. This should be 100 C. 100 C. I fix it. So this should be 100 C, right? 100 Celsius. So this one should be removed. Okay. So for the H9, which is nitrogen at 150 C, so we have to do interpolation as you see. If we do interpolation 2.19 plus 5.13 divided by 2, that is just 3.66. Okay, we find out H3, H9. So H6 and H7, which is this one, right? So H6 is for the carbon dioxide from 25 degrees Celsius to 150. Right, so heat of formation of carbon dioxide plus integration 25 to 150 Cp carbon dioxide dt. Where do we find out this information? That from the tablet B1, right? Carbon dioxide heat of formation. Let's take a look. Carbon dioxide, carbon dioxide heat of formation. You see, we're talking about the gaseous phase, right? So that is a negative 393.5. So you get the number here, right? And then this term, since carbon dioxide can be found out in tablet B8, we just use tablet B8 for the 150, which we have to be interpolation. So we're going to use 100 and 200 average value for the carbon dioxide. And then you see carbon dioxide, right? 100 and 200 value. And we find out the average of this one. That is 2.90 plus 7.08 divided by 2. So now, if you calculate all of these, we have H6 as a negative 388.51 kilojoule per mole. For the H7, we talked about this, right? That is a water. So again, you use this formation, right? That is heat of formation of water plus integration 25 to 150 degrees Celsius Cp water dt. This one we find out from table B1, right? So if you go table B1 for the water, table B1 for the water is here. Oh, no, sorry. Heat of formation, right? So have to be, we talk about gaseous vapor phase, right? Not liquid. So that is negative 241.83. So you're writing down number here. So this term, since we find that this water in table B8, we're going to use pre-calculated number, and then that is interpolation. So 100 and 200 divided by 2 average. So if you calculate overall, we find that HS7 as a negative 237.55 kilojoule per mole. Okay, so we find out these, the information we haven't find out is the H1 and 4 and 5. Let's find out these. So for the H1, again, you use the same equation as you see here, right? So then H hat 1 is going to be heat of formation of methane plus integration 25 to 25 Cp methane dt. H1 is, as you see, this one, right? The condition is 25. So from reference to 25. So that's why you see integration 25, reference to desired temperature, Cp methane term. As you see, this term should be 0, right? So we only need to read heat of formation of methane. That can be found out tablet B1. So methane tablet B1 is methane CH4, as you see here. We have heat of formation as negative 74.85. So you're writing down this one, right? Negative 74.85, this time is 0. So we find out H hat 1. For the H hat 4, it is methane, but now our desired temperature is 150, right? So we're talking about this one, condition is 150. So from 25 to 150. So the equation is going to be delta H, not heat of formation methane, integration 25 to 150 Cp methane dt. So this one, we already find out number as negative 74.85. So you just write down here, integration 25 150 Cp methane dt. We cannot find out the methane in tablet B8, so this one we have to use tablet B2. Let's assume since tablet B2 for the methane, let's take a look. So for the methane, you see here methane, right? So and then we talk about the gas and then Celsius, right? So we're gonna use this A, B, C, D term. But since the B, C, D term is a lot smaller than A term, we assume we ignore these three terms to make calculation easy. So it's going to be we're gonna take 34.731 multiplied 10 to the negative 3 for as a CP term. So you see it here, it's going to be negative 74.85, which is the heat of formation plus integration 25 to 150, and then 0.03431 dt. This is easy to calculate, right? Basically, this term is a 0.03431 multiply 150 negative 25. So if you calculate this one, we have 4.28875. So if you calculate this one, we find out H hat 4 as negative 70.56125 kilojoule per mole. Okay, we complete H4. The last one, we haven't found the H hat 5, which is about formaldehyde from 25 to 150. Right, so that is formaldehyde. Is it this one, right? So formaldehyde heat of formation plus 25 to 150 Cp formaldehyde dt. Again, this one can be found out in tablet B1 formaldehyde. Let's go tablet B1 formaldehyde. Forum. Here, right? Formaldehyde, we have negative 115.90. So you write down negative 115.90 formaldehyde. And for the this term, again, we gonna BCD term to make calculation easy. And then we find out so let's take a look at ABC term. So table B2, formaldehyde. Formaldehyde is, do you have number? Do you have a number? Okay, so this one, right? Formaldehyde gas space. So we have number here, but we're gonna ignore this BCD term. So we're gonna use this term, 34.28 multiplied 10 to negative 3. That is 0.03428, right? So if you plug in A here, the equation becoming this. This is easy to calculate. So this term is of 0.03428 multiply 150 negative 25. So this whole term is 4.285. So if you plug in the number, we find out we have H hat 5 as a negative 150.90 plus 4.285. So if you calculate it, we have negative 111.6 kilojoule per mole. So we almost complete. So delta H is a sigma N out multiply N hat out minus sigma, not sigma, sorry, excuse me, sum of N out multiply H hat out minus sum N in multiply H hat in, right? So take a look. So basically this is out, right? And this is in. So this plus multiply this plus 30 multiply H5 plus 10 multiply H6 plus 15 multiplied H7 plus 15 multiplied H8 plus 376 multiplied H9 minus 100 multiplied H1 minus 100 multiplied H2 minus 376 multiplied H3. That's what you do, right? So if you plug in the number, as I just said, right? And then if you do calculate, we have answer as 15,000, negative 15,341.73 kilojoule. Unit is a kilojoule, right? Because this is a kilojoule per mole, and then this is mole, so mole can start. So we find the Q, which is delta H, as this number. So we complete to solve this example 9.5-2. That is a multiple reaction case. So let's take a look at another example. That is a single reaction, but the difference, this is a very similar problem, but difference is here we're gonna compare the case. So actually we can solve this problem exactly the same method as we used previously, or we can solve slightly easier if we use a hero reaction method, right? So this is a reaction. Before solving it, let's read the problem together. Okay, so here is a problem we solve. That is, this is a example 9.5-1. This is energy balance on ammonia oxidizer. The standard heat of reaction for the oxidation of ammonia is given below. Right? Ammonia react with oxygen, produce nitrogen oxide and produce water, and then heat of reaction is given as this number. 100 mole of ammonia per second, so this is mole rate, right? The mole per S, and 200 mole of oxygen per second at 25 degrees Celsius are fed into a reactor in which the ammonia is completely consumed. So there will be no ammonia remaining. And the product gas emerges at 300 degrees Celsius. So this is a 300 degrees Celsius, but coming in is a 25 degrees Celsius. Calculate the rate at which heat must be transferred to the to or from the reactor, assuming operation at approximately 1 atm. So basically, we need to find out the Q dot, right? So that was the problem. So if I drew the flow chart, this is what it look like. I just rewrite, repeat the reaction, and then heat of reaction number, right? This is pipeline 1, pipeline 2, reactor, right? And then this coming in is given. So we have ammonia coming in as 100 mole per S, and the oxygen coming in 200 mole per S. The temperature T1 is 25 degrees Celsius. P1 is 1 atm. And this is our goal. We need to find out how much heat is in or out. And then for what we know is ammonia out is 0 because it mentioned that see, ammonia is completely consumed. So what we know is the ammonia is 0 mole per S. And then all other species at the pipeline 2, which we don't know yet, right? So oxygen, nitrogen oxide, and water, we don't know yet. But we know the temperature of pipeline 2 is 300 C and P2 is 1 atm. So let's do material balance first. Since there ammonia, we know in and out, and then we know it's a corresponding coefficient. So that means we should be able to find out the extent of reaction. Extent of reaction is not a function of species, but only function of this reaction. So per reaction, we have one single extent of reaction. If we find out extent of reaction of ammonia, that should be same as extent of reaction for the water, oxygen, and nitrogen oxide and water. So this we already run, right? So extent of reaction by definition is a reacted amount, which is N out minus N in. You normalize by corresponding coefficient. So out is 0, right, here. And then in is 100 mole, right? And then corresponding coefficient for the ammonia is 4. -4 because this is reactant, right? So if you plug in the number, we find out heat of extent of reaction is 25 mole per S. Actually, sorry, there is the mole per S. So we find out the xi dot. Okay, so once you find out the xi, since this xi for the ammonia, oxygen, nitrogen oxide, waters are all same, so we can use this reaction to find out all of these three to complete the material balance. So N out is going to be N in plus xi multiply nu, right? If you apply these to the oxygen, and oxygen pipeline 2 is going to be coming in, which is 200 oxygen, right? Plus the heat of extent of reaction, which is 25 multiply oxygen you see here, right? So 5, but this is reactant, so -5, right? So 25 multiply -5 is so 200 plus 25 multiply -5 is a 75 mole per S. So we find out this as a 75 as a N out option. N out nitrogen oxide is in plus heat extent of reaction multiply nu. So this, right? Nitrogen oxide is product, so it's going to be +4. So 25 plus 4 multiply plus 4 is 100. So you're writing down this as 100, right? For the water, 0 coming in, but and plus extent of reaction, which is 25 multiplies 6, right? So then we have water as a 1/5 mole. So we complete the mole balance, right? So we find out all we need. Okay, the goal, as we mentioned, is find out the Q, right? Q dot. So Q dot is from energy balance is WS, Q dot minus WS equal to delta H dot plus delta EK, which is a kinetic energy plus potential energy. So these three terms goes to 0, right? So delta Q dot is going to be simply delta H dot, and then we're going to use this general equation that we learned. Or we can use xi term, but you will see the difference. But let's stick with the general equation first. So this one. So we're going to use exactly the same method as we just used for the 9.5-2 method, right? Okay. So, okay. So let's start with the NH table. So this is a case without using heat of reaction. But later, I'm going to show you the method using the heat of reaction method too. Okay. So here we have reference, species, phase, N in, N out, H out, right? For the species, we have ammonia, oxygen, nitrogen oxide, and water. And phase, we know all gases, and this is phase. And then we already complete the material balance, this part, right? So if you plug in the number, 100 more ammonia coming in, 200 more oxygen coming in, and then we don't have these two components at the very beginning. At the product line, we consume all ammonia, but we have 75 moles of oxygen, 100 moles of nitrogen oxide, and then 150 moles of water. Okay, so since this is 0 term, right, that means we don't need to find out these three H hat, so we cross out. So H we need to find out is only H1, 2, you just name it, 3, 4, 5, right? Okay, so let's start with the H1, H hat 1. H hat 1 is ammonia. The reference state is going to be 25 degrees Celsius and 1 atm. I forgot writing, let's write down here. So that is going to be 25 degrees Celsius, 1 atm. Okay. So H1, we look H1. So we talked about this equation, right? So this is very general equation you can always use, right? So basically, H hat I means a species, is a heat of formation of that species plus integration 25 degrees Celsius to desired temperature. 25 because this is our reference state, right? For H1, H1, this is about ammonia. So it's going to be ammonia hero formation plus integration 25 to what is the temperature incoming. So this one, let's review. You see temperature coming in is a 25 and then coming out was 300. So this is all 25, right? This is 300C. So for the H1, it's going to be from 25 to 25C, right? So we have keto formation, integration 25 to 25C, CP, ammonia, DT term. And then as you see, since this is the 25 to 25, this is going to be 0. So we only need to find out keto formation of ammonia at 25C. Where we find it? Table P1. So if you go table P1, we talk about ammonia, right? So 3 ammonia, we have hero formation, right? We talk about gas. That is a negative 4619 kilojoule per mole for ammonia. So you just plug in the number, right? This one. So we find out H1, H hat 1 as a negative 4619 kilojoule per mole. So for the H2, we use same equation, right? That is going to be heat of formation of oxygen from integration from 25 to 25 CP oxygen dt, and then this is going to be 0. And then if you take a look at the heat of formation and oxygen, it is also 0 too. Table B1, oxygen, right? That is 0. So you plug in the number. So we find out H hat 2 is 0. So this one is 0. Okay. H3 is about oxygen from 25 to 300, right? So heat of formation of oxygen plus integrand 25 to 300, right? CP oxygen dt. So we just find out this is 0. So this is not going to be 0, right? How do we find out this? We can use pre-calculate integration value from table B8 or table B2. But if you find out the species in table B8, that is much easier because it is pre-calculated. So we just need the value. We just need to read the value at 300. So if you go table B8, we're talking about oxygen, right? And 300, sorry, 300, this one. So it is going pre-calculate number for the integration term is going to 8.47, right? So this term is 8.47. So if you plug in 0, 8.47, so we find out H hat 3 is 8.47 kilojoule per mole. Okay, now H hat 4, it is about nitrogen oxide at 300C, right? From 25 to 300C. So somehow it's removed. So 25, so it is going to be 25C 1 atm, right? So H4 is a 25 to 300. So we have hero formation of nitrogen oxide and then 25 to 300, right? So this coming from tablet B1, right? This, if you can find out tablet B8, we just use it, but we don't find it carbon, nitrogen oxide in tablet B1, so we have to use tablet B2 for this one. Right, so let's take a look at the tablet B1 first for the carbon nitrogen oxide. You see it here, right? So heat of formation is a 90.73. So you're writing down 9.73, right? So this term, CP term, we have to use ABCD, but let's ignore BCD term because this contribution from BCD is a lot smaller than A. So we just assume it. There is an error, but it's okay. So C, so there's, we talk about B2, right? And then nitrogen oxide, where is it? Here, right? Nitric acid, sorry, nitric acid, right? And you see this is A, B, C, D term, but we ignore this B, C, D term. So we only take this one, 29.50 multiplied 10 to the negative 3. right? So here, right, is going to be 0.0295 multiply 300 negative 25. So if you calculate it, we find out H hat 4 as a 8.11 to 5 kilojoule per mole at this term, right? So if you plug in the heat of formation information here and this term, we find out H hat 4 as a 98.4825 kilojoule per mole. And finally, H5, we're talking about the water, right? So we're going to use tablet B8 because B8 include the water that is from 25 to 300. So again, heat of formation water, 25 to 300, right? This one from tablet B1, this one from tablet B8. So if you find the number, it is going to be, let's do that, water, right? We talked about 300. We talked about the heat of formation water. So heat of formation water, we talked about the vapor phase, right? So negative 241.83. So if you go here, right, negative 241.83, that is a heat of formation of water, right? And this term, we're going to use tablet B8. Just need to read the 300. So B8 water, right? 300, that is a 9.57. That is pre-calculated integration term. So all of this number you type in here, right? So HF5 we calculated as negative 232.26 kilojoule per mole. You see so far, the method we using is exactly the same as previous one. So that's why I said this is general method. So let me go back. So you see these two methods. This is more generalized method. This is a method. This is an equation you can use if you know the heat of reaction. There is a benefit. You will see soon. But what you're doing right now is we sticking with the general method. This one, right? Okay. Now we find out everything. Now we find out everything. Where is it? Okay, here, right? H hat 5, we find out this one. So we find out all number. So finally, what you need to apply is this equation, right? So that's going to be delta H dot is going to be sum and dot out, H hat out minus sum and dot in multiply H hat in. So it's going to be this multiply this plus this multiply this plus this multiply this, right? Minus 100 multiply H1 minus 200 multiply H2, right? If you do that, this is number, and then you have negative 19,735.5 kilojoule per S. That is delta dot H, which is same as delta if you do that, this is the number you have, and then if you find out, if you calculate it, we have negative 19,736 kilojoule per S. So our answer Q dot is going to be this number. Okay, that is generalized method without using heat of reaction. But let me show you the benefit of using heat of reaction. Basically, heat of reaction is, as we learn, heat of reaction already include heat of formation information. So when you calculate, when you plug in this heat of reaction, we don't need to worry about heat of formation. Let's say, right, this is a equation we use, and then we don't need to worry about this, right? So let's do that. So H1, right? H1 was this one, right? So that is going to be 25 to 25C, right? So that's going to be 0. And H2 is oxygen, right? That is 25 to 25. That is going to be 0. You see, we don't worry about the heat of formation number here. So because we are going to use a heat of reaction. So H3 is going to be this one, right? So that is oxygen from 25 to 300 C, right? So H3 is integrating 25 to 300 CP oxygen DT. And then we can find out this value from table B8, oxygen 300, right? So oxygen 300, that is a 8.47. So you just plug in the number right here. And H4, again, we don't need to worry about the heat of formation number since we're going to use heat of reaction. So H4 is this one, right? We talk about nitric oxide from 25C to 100C. No, to 300C. So here, integration 25 to 300 CP nitric oxide DT term. So again, let's assume BCD contribution is really small. So we only take the 8 term, which we can find out table B2, which is 0.0295. So all of this term is simply 0.0295 multiplied 300 negative 25. So we have number HF4 as 8.1125 kilojoule per mole. Lastly, H5 is about the water, right? And again, we don't need to worry about heat of formation since we're going to use heat of reaction. So H5 is going to be interaction 25 to 300, right? 25 to 300 for the H5, right? CP, water, DT, and then this is a specific, special molecule that we can find out table B8. So if you table B8, 300 water, so we turn on water, right, 300, so we have 9.57. So here, 9.57. So we complete. So now the equation, so this is specific, the equation we can use if we want to use heat of reaction, right? You see the difference, this, we're comparing this with this one. The goal is basically use both equations to find out delta H, right? Delta H. But this one is more generalized. But this one only work with the heat of reaction is known. Anyway, so all of these terms is we already find out, right? This one we find out above, right? This is a given. We find out N and H. So if you plug in the number, right? That is going to be this one, negative 25 heat of extent of reaction, right? The value heat of reaction was given as a negative 904.7, right? So N out minus N in, that is going to be this multiply, right? This multiply this plus this multiply this plus 150 multiply H5 minus 100 multiply H1 minus 200 multiply H2. Then if you do that, right? So I'm talking about this one, right? So this out and this is in with extent of reaction. Then we have number negative 19,735.5. Let's compare this value with the previous one. That is, where is it? That is this one, right? You see the value is very close. The generalized method, we have 19,736 here, 19,735.5. So it is very close. So either way, it's your call. You can use either method, but bottom line is if heat of reaction is given, just use it because it is more simple. But we can omit the heat of formation term. But if heat of reaction is not given, then we need to add heat of formation term for all calculation H hat I. So that completes the solving these two examples, which is extremely important. And I highly recommend to review these two lecture notes and understand well. And then if you have any question or difficulty, please feel free to stop by my office or send me an email. Okay, and this is a homework and good luck for preparation for the final. Thank you.